Hello, folks. Well, Darui wants to make sure we make our final connection to cell potential and, this time, concentration. So he states, standard state conditions are often considered, but real cells start with different concentrations, and the concentrations change during cell operation. So to determine the cell potential in non-standard states, okay, we derive an expression by relating delta G in its non-standard state. So from chapter 16, our expression for non-standard free energy is going to be delta G is equal to standard delta G plus RT natural log of Q. Now what we want to do is now plug in our relationship of delta G and cell potential, and we can write negative NF, non-standard cell potential, is equal to negative NF, standard cell potential, plus RT natural log of Q. Now, of course, if we only want to focus on cell potential, we would divide this entire thing by negative NF, and that will get us this overall expression, which is non-standard cell potential is equal to standard cell potential minus RT divided by NF natural log of Q. And this expression is called the Nernst equation. Yes, the same Nernst from chapter 16 who formulated the third law of thermodynamics. Again, it states non-standard E of the cell is equal to standard E of the cell minus RT divided by NF natural log of Q. And it allows us to relate non-standard cell potential to now concentrations within a redox balance reaction. So how do changes in Q actually affect cell potential? Let's get into it. Well, when Q is less than 1, what does that mean? Well, first I got my Q ratio here. Q is equal to the concentration of products divided by the concentration of reactants, or the partial pressure of products divided by the partial pressure of reactants. We know that we're not going to be using solids and liquids, for example, right? So we're dealing with things that are aqueous or gaseous, et cetera, et cetera. Now, when Q is going to be less than 1, that means the reactant concentration is way larger than the product concentration. So therefore, the natural log of Q is going to be less than 0. We also know and see that our standard cell potential and our E of the cell rely on one another, right? So if this entire thing is going to be less than 0, then guess what? Our non-standard cell potential is going to be greater than our standard cell potential under these circumstances. Now, when Q is equal to 1, and thus the reactant concentration and the product concentration are equal to one another, then the natural log of Q is equal to 0. So when the natural log of Q is equal to 0, this entire portion of this expression is now equal to 0. So our non-standard E of the cell and our standard E of the cell are equal to one another. And then, of course, finally, when Q is greater than 1, that means we have way more products than we have reactants. And so our natural log of Q is also going to be greater than 1. And when this is a greater, larger number, according to this one, of course, attached to this one here, then guess what? Our non-standard E of the cell is now going to be less than our standard E of the cell. And so these are some kind of relationships we see about how Q can affect cell potential. But never forget that the Nernst equation helped us directly see and relate not only our concentration, but also our standard cell potential and our non-standard cell potential. This is very powerful information, folks. All right, folks, so Daruri has again given us another expression to make even more strong relationships. But of course, we want to make an expression that's going to give us the best, most suitable expression for calculations, right? And of course, that means taking things that are natural log and put them into log form. And so we can take our overall Nernst equation. Again, we're going to make sure that we multiply everything here by 2.303 to go from natural log to log. We're still going to have 8.314 for our R value. We're still at 298 Kelvin. We still don't know what our N value is. And of course, we know our Faraday's constant. And of course, we are now trying to go from natural log to now log of Q. So we plug all these numbers in, and guess what we get? This expression here, which of course is the exact same as the Nernst equation. It's just one that's easier for calculations. So you're going to say non-standard cell potential is now equal to standard cell potential minus 0.0592 volts divided by N log of Q. And this is, of course, at 298.15 Kelvin. Now let's chat. What's really interesting in using this equation is when you actually need to solve for Q here, it only contains species with concentrations and or pressures. So, for example, if I'm given concentrations for aqueous ions, then I will use those concentrations. So I'll say, okay, I have my 1 molar here. I have another, for example, 1 molar here. Great, I got my concentrations of my products and my reactants. But if I'm also given partial pressure, like say I'm given partial pressure of H2 gas because I'm using a standard electrode or sheet cell, right? Then I actually can multiply my partial pressure to my overall concentrations as well. In essence, whatever concentrations or atmospheric amounts that you're given for the species in these balanced redox reactions, you can use to solve for Q here. Now, of course, you're still going to exclude pure solids and liquids, meaning you're not going to add in solids or liquids to your overall calculation. That still stands. But this is a little bit different from what we know when it comes to Q. We're always used to separating. We have our concentration or we have our partial pressures. With electrochemical cells and using this Nernst equation here, doesn't matter if you have molarity and partial pressures here, you're going to multiply those numbers together. And it also worked out because Q does not have units as well. All right, folks? So we have officially completed our understanding of the voltage seal jitsu. From learning the construction, operation, and notation from the fourth grade Kage, to understanding cell potential, and standard half cell potential with killer B, to now finishing up the relationship with cell potential, free energy, equilibrium constant, and concentration with Darui, we have done it. Let's get to the training grounds for a final example. So we are back to the voltaic training grounds for the last session as we wrap up our time in this village. This says we're going to be using the Nernst equation to calculate non-standard cell potential. So in a test of a new reference electrode, a chemist constructs a voltaic cell consisting of zinc/zinc 2 plus half cell and a H2/H plus half cell under the following conditions. They give us the zinc 2 plus concentration of 0.01 molar and the H plus concentration of 2.5 molar and the partial pressure of H2 at 0.30 atmospheres. They want us to calculate the non-standard cell potential at 298.15 Kelvin. They also gave us the half cells here. So of course, we got to get our minds working. We got to think about everything we learned from Killer B, everything we learned from Darui, and put it all together. All right, folks? But of course, this all connects to everything we learned with the fourth grade Kage as well. So first things first, let me go ahead and write my overall reaction I'm going to be using, my Nernst equation. All right, non-standard cell potential is equal to standard cell potential minus 0.0592 volts divided by the number of moles transferred in the redox times log of Q. All right, let's get to it. Now, what do we need to do? We need to make sure we have everything to be able to fill out this overall expression. So how do we get our standard cell potential? Well, we already know that E naught of the cell is going to equal to E naught of the cathode minus E naught of the anode, right, folks? And so we can look at our half cells and figure out exactly which ones are which. First, we have an E naught of the cell potential of 0.00 volts, and then we have negative 0.76 volts. So that means that whichever one is going to be more positive is going to be reduced, and of course, at the cathode. So we have this at the cathode of 0.00 volts, and then of course at the anode is going to be oxidation. It's already reversed, as we can see here, and that's going to be negative 0.76 volts. All we have to do is plug it in here. So our cathode is going to be 0.00 volts minus our anode, which is going to be negative 0.76 volts, and that is equal to 0.76 volts. So we have our standard cell potential. Now we also can look at the number of electrons that are transferred. There are 2 here and 2 here, and so that means our N value is going to be 2 electrons. We have this value and this value. Now to get Q, you don't want to just jump in all willy-nilly and start just plugging in numbers. You want to make sure you have an overall reaction that is balanced so that you know what's going to be the reactants or products, so you can put this in your Q and get the ratio properly. So let's go ahead and do that. All right, so we have 2H plus Zn solid is going to give us H2 gas plus Zn2 plus. Now we know gaseous and aqueous forms we can use, but solid is not going to be part of our Q value. So our Q is going to equal to our products divided by our reactants. Our products are going to be our H2 gas, which has a partial pressure of 0.30 atmospheres, multiplied by our zinc 2 plus, which has a concentration of 0.010 molar. This is all going to be divided by our reactants, which we know we do not use a solid, so it's only going to be H plus here. And that H plus is going to be 2.5 molar. And of course, because there's a 2 in front of it, we have to make sure that everything is balanced. So this H is balanced, this is balanced here. Our zincs are balanced, so there's a 2 in front of here. We have to square our 2.5 molar here. Now, all the left to do is to calculate, plug and chug here. All right, so when I multiply my numerator, I get 0.0030 When I take my 2.5 and square it, I get 6.25. When I divide these two numbers, I get 4.8 times 10 to the negative 4. Now I'm going to go further because I know I have to take the log of Q. So I'm going to take the log of this 4.8 times 10 to the negative 4, and I get negative 3.318758,763. Now I have this entire value, this value, and now this value. All that's left to do is start plugging everything in. So when I plug everything in, I get 0.76 volts minus 0.0592 divided by 2, multiplied by negative 3.318, of course, this long number. Now, what I tend to do first, of course, is going to be doing my division. Once I did my division, I got 0.0296, and then I multiplied this number by the negative 3.318 number, and I got negative 0.098235259 volts. Now, of course, this number is negative. Now, in order to finish off the expression, I'm going to take 0.76 volts minus my negative number here, which means they're going to be added together, and I get 0.86 volts as my final answer, which is going to be the non-standard cell potential for this question, folks. And that's it. Thanks to the Hidden Voltaic Village for our journey in teaching us the voltage seal jitsu. Back to the Hidden Chemistry Village to see our ranking and get our next mission, folks.